So yeah, thanks Chua for the very embarrassing introduction, the very nice introduction, and thanks very much for inviting me to speak today. So I was honoured a couple of weeks ago to speak at the National Emergency Briefing, and I will say that if you haven't signed the letter to Keir Starmer yet, then please do so, and please try and get other people to sign as well, because I think we are facing a climate emergency. Hopefully you'll see that in what I'm going to show you today, that we are experiencing already record-shattering extreme weather events, and we are seeing a rapidly changing climate. And we really do need to do something about this very fast. So without further ado, I'm gonna start with the story of where the title of this talk comes from, and it was very much from the summer of 2021, and I'll talk quite a bit about the summer of 2021 for the next few minutes. You'll all remember the German floods that happened and caused over 200 deaths. I was involved in a rapid attribution study at the time, and we found that global warming had made the heavy summer rainfall more likely and a lot more intense as well. And this precipitated an inquiry by the Joint Committee on National Security Strategy, led by Dame Margaret Beckett, where they looked at whether the UK was ready for these types of storms, and whether our critical national infrastructure was well, fit for purpose in this age of climate change. And one of the things that I said at the National Emergency Briefing just a couple of weeks ago is really that our critical national infrastructure is not fit for today's climate, never mind tomorrow's climate. And this is very much coming from this report, where they called the government to get a grip on climate change impacts, overwhelming evidence that climate change is already having an impact on UK infrastructure, and that we must finally recognise that prevention is better than cure, and move on from this dangerously reactive approach to risk management. Now, this was in 2022 that this was reported by the Joint Committee on National Security Strategy, and there's been very little happen since. And so we're now 3 years on. We're still not really treating adaptation and resilience with the seriousness it deserves, and we're obviously not treating emissions reduction with the seriousness they deserve either. So why should we be concerned about these record-shattering rainfall extremes? And I've put there at the top, living in a 1.3 degree C warmer world. But you can see how quickly things move on, because Copernicus reported yesterday that we expect that the last 3 years will exceed for the first time 1.5 degrees of warming. Most climate scientists would tell you off the record now that the idea of trying to stay below a 1.5 degree Paris target is gone, and that we really desperately need to try to remain below that 2 degree target. And because of that warmer world, we're seeing these record-shattering rainfall extremes. And you'll remember another big blocking, slow-moving storm, a cut-off low, like the German floods, but this one was in the summer of 2023, where Storm Daniel hit Greece, producing a huge amount of rainfall, 760 millimeters of rainfall in just a day. So that's 3/4 of a meter of rainfall, and that's the same amount that fell in Valencia actually last October as well, again in a day, but produced over a meter in over 3 days. And the other thing about this storm is that it was huge in scale. You can see it on a satellite image there. It flooded 730 kilometers squared, a fifth of the agricultural land in Greece. It then went offshore into the Mediterranean, and it became a medicane, which I had never really heard of before, but it's a hurricane in the Mediterranean. Because those sea surface temperatures were so warm, it became a hurricane, it reinvigorated the storm, and it hit Libya. And they had a huge amount of rainfall in just 6 hours, which basically caused 2 dams to overtop. And I think there's estimated they still haven't found about 8,000 people, but they said there were about 5,000 known deaths from that event. So huge events. There was a similar storm in Spain as well on the other side of this omega block, this heat wave with 2 cutoff lows on either side, which again caused huge amounts of rainfall in just 24 hours and serious floods in Spain at the same time. And it caused a number of devastating floods around the world from the 3rd to the 10th of September 2023. And I think that when we summarize this in a review paper in Nature Reviews Earth and Environment for the state of the climate, the review of the climate for the year, we really, one of the things we said was key was this blocked wave pattern causing slow moving cutoff lows. And there's a number of other things as well. You know, we're seeing intensification of tropical cyclones across the world. We've seen this recently, obviously, in Indonesia, an unusual tropical cyclone hitting there. And we've seen huge numbers of severe convective storms, and they're actually the major cause now of insurance claims and these billion-dollar events in the US over the last few years are now from convective storms. They previously weren't. And, you know, these events used to be unusual. But again, one of the things, and this is one of the slides from my briefing in Westminster Central Hall a couple of weeks ago, these events are no longer rare, right? They're happening again and again and again. And this is Storm Boris last year, September 2024, huge amounts of rainfall. Falling in Central and Eastern Europe, caused the collapse of 3 or 4 dams again. And again, just after this, in October, we had the huge rainfall event in Valencia, which killed over 200 people. These events are becoming much more common. And September and October last year was again marked by these blocked wave events around the Northern Hemisphere and massive floods and heat waves because of this. And what I'm going to talk about in this talk is this is a slide that was produced by Paul Davies, who was formerly at the UK Met Office, but he's now working with me at Newcastle University on my new fellowship. And within that fellowship, actually, we're thinking very much about these blocked wave patterns, which you can see show it here. So you can see these high pressures and then the low pressures in between. See this very blocked pattern in the Northern Hemisphere. And that pattern causes a number of different persistent weather extremes. And you can see it causes heat domes. You can see examples in the US, the North American heat dome there, and the Siberian heat dome and wildfires. And then also some really big flood events in Germany and in China, in Zhengzhou, and a very intense rainfall event in New York. And all of these events happen in sequence with the energy movement of this blocking pattern. So I'm going to talk about why that's important as I go through the talk, because when we think about these types of extremes, we really treat them in silos as scientists. We either work on regions or we work on particular types of extremes, like we might just look at heat waves. But actually, I'm going to argue that all of these are linked in space and time, and we need to be thinking about how they occur in sequences and in space and time. But before I do that, I'm going to go back a little bit, and I'm going to talk about how advances in high resolution data sets, in observations and in climate models have helped us to understand changes to extreme weather. Hopefully the slide will move on. Good. So I've worked on these types of models for quite a long time now, and since we started developing these with Lizzie Kendon at the UK Met Office, not quite 20 years ago, but certainly 15 years ago now. And we were able to run a weather forecast model for the first time as a climate model. And one of the reasons that we're interested in doing this is because coarse resolution climate models and convection parameterized climate models, like you see there in the sort of middle plot, the 12-kilometer resolution model, really weren't able to tell us anything about changes to heavy rainfall in the summer. They just didn't have a signal of change. The PDF was very much centered on 0. Whereas when we use a weather forecast resolution model and we force it with greenhouse gases, it's able to resolve shallow convection at least, and it produces very different predictions of future change. And with this, the UKV, the weather forecast model that we forced with greenhouse gases, we're able to show that hourly events over 30 millimeters show a 5-fold frequency increase by 2080. And this was published in a paper led by Lizzie Kendon in 2014. So they've revolutionized climate modeling, and there's now a huge number of groups all over the world that use these very high resolution climate models, which explicitly represent convection without the need for a parameterization scheme. They have a grid spacing of less than 4 kilometers. There's continental scale domains here now, and you can see on the right of the screen an example of a European convection permitting model simulation at 2.2 kilometers at the top, and then the 25-kilometer global model simulation at the bottom there. So we've done lots of work on this, and lots of other groups around the world have done lots of work on this, and we found that they produce more realistic rainfall intensities, extremes, rainfall durations, frequency of events, and the diurnal cycle is much improved. And we've done more work recently looking at other things like whether they are able to represent extreme wind gusts, hail, and lightning, and I'll talk a little bit about that in this talk as well. So what do we know about changes to rainstorm characteristics? And some of this has come from observational studies, and some has come from these very high resolution climate models that we've been running. And again, it's from various groups around the world. But when we look at changes to rainstorms, we now understand that the most intense part of the storm will get more intense. And you can see a really nice paper that was published by Conrad Wasko and Ashish Sharma there in Nature Geoscience in 2015, using observations. They split the storm up into 5 equal durations and looked at how that the storm became more or less intense with warming. And you can see that the red bits of the storm became more intense and the blue bits became less intense. And that's been substantiated in other work as well. You can see that reference there. We've also found recently that storms become more front-loaded with warming as well. Visser et al. Did some work on this in the Journal of Climate in 2023. We've done some work on this running convection permitting models over Germany as well. There's also changes to storm size, and this is very much dependent on changes to moisture availability and large-scale dynamics as well, which affects convective organisation. So in places like the UK, where there's no limit on moisture availability, very much the storms get bigger and they get more intense as well. In other places, they perhaps become smaller. If there's limitations to moisture, they become more intense but become smaller in size as well. And this was supposed to be animated, but anyway, I'll tell you what it was supposed to say. So the other thing we found is that storms become more slow moving as well as climate warms. So there's a very nice study that was done by one of my postdocs, Abdullah Karaman, which was published around the same time as the German floods in 2021, that showed that storms become more slow moving in the future warmer world as well. And this is partly to do with the fact that the jet becomes weaker and a bit wavier as well because of this reduction in the temperature gradient between the equator and the poles. And that's to do with the Arctic amplification effect. And of course, when we get more slow-moving storms, they sit over one place for longer, and we get the flood effects that you see here. So we also have done some work recently thinking about operational attribution and looking at how individual rainfall events, the intensity of rainfall within those events might change at different warming levels. And this is some work that's been operationalized now by the Dutch Met Service and led by Geert Lenderink and published just this year in Weather and Climate Extremes. And this shows an example of an event in Italy. And you can see that we simulated, we've basically taken reanalysis data and used that as boundaries on a convection-permitting resolution model and simulated the event within that domain that you can see. And that produces a realistic representation of the rainfall event for the present climate, which can be checked against observations. And then we've also looked at a 1.5 degree warmer world and a 3 degree warmer world. And you can then see how that event might be different in a warmer world, or indeed how it might have been different in a pre-industrial world. You can see that past minus 1.5 degree world as well there. And some of the interesting things that we found, I suppose, are that you can get these really, really very high scaling coefficients in rainfall. So up to 20% increase in the intensities of rainfall. And even across the whole event, you can get something like 12% increases. So they're very much super Clausius-Clapeyron increases. So Clausius-Clapeyron theory tells us that the moisture of the atmosphere, as the atmosphere warms, for every degree of warming, the atmosphere can hold 7% more moisture. And that's normally the rate at which extreme rainfall scales. But we find that actually we can get much bigger increases in the intensity of rainfall from warming in the models for these types of events. And that's quite worrying. And I'll talk a little bit about that later. So there's also changes in lightning that we've looked at as well. So we've been able to use convection-permitting models to look at changes in lightning. Again, this is a study that was led by my postdoc, Abdullah Karaman, who's based out at the UK Met Office. And he looked at how lightning might change in the future climate. And you can see for the UK, for example, you get more lightning in the summer over land. But interestingly, over the North Sea, much more lightning in winter as well. And then you get more lightning over higher elevation, and particularly in the Mediterranean in the autumn as well. You get much more lightning than currently. The other study that we've done recently, which only came out a couple of months ago or something, in Nature Communications, was again led by Abdullah Karaman, and he looked at how climate change is changing hail across Europe. Found that climate change is supercharging Europe's biggest hail. So, I mean, this is, I guess, there's often some very subtle messages with climate change, and in general, we expect hail frequency to decrease because of the increase in melting level height. Increasing warmer temperatures in general produces fewer incidences of hail. But what we did find is that when we do get big hail storms, we may get much bigger and more devastating hail from these storms. And we've seen a little bit of this recently. There've been instances where aircraft have been damaged quite significantly by hail, houses, cars, that kind of thing, particularly in southern Europe. And one of the things we found is that you start to get these warm type thunderstorms that we don't get in the current climate in Europe, but we do in the future climate. And these are the types of things that we only find in the tropics at the moment, but they produce very, very large, very impactful hailstones. The other thing we've used the models to look at are in the winter. Colin Manning, again, one of my postdocs who's based down at the UK Met Office, has looked at whether we can use these models to examine changes to extreme windstorms in the winter, and particularly something called sting jets. Now, sting jets are very impactful when they happen. There was a sting jet in Storm Eunice in February 2022, for example. There was one in the Great Storm in 1987, if people remember that. And it's something that a very, very fast flow of air that descends from the mid-troposphere inside the cloud head. And it hits the ground, a very narrow band of wind, but very, very devastating, very, very high winds, a few 100 meters to a kilometer across, and yeah, causes big impacts. So what we found when we looked at this is, yes, with a convection-permitting model, you can actually find the evidence of sting jets. You can see these signatures of sting jets. And actually, we find that in the future, we get many more of these Shapiro-Kaiser warm core storms. And a lot of these also contain sting jets as well. And so we get quite significant increases in the most extreme winds in the future from these winter storms. The other thing is we looked at compounding events in the winter, and we find that extreme wind and extreme rain increases. So the land area experiencing both increases in the future. And of course, this is a problem, right? Because when we get extreme winds in the winter, and we've literally just seen this with Storm Bram that was in the UK yesterday and Ireland as well, you get high waves, you get storm surges, but you also get inland flooding as well from the rainfall. So wind causes damage to energy networks as well, and sort of combined, they're not a good thing. So I'm going to talk a little bit now about whether changes to large-scale circulation dynamics matter for changes to extreme weather. And again, talk more about this blocked pattern that I talked about at the start, which causes these persistent weather extremes globally. So I'm sure that all of you remember the summer of 2022. So the blocked conditions that we saw in 2021 led not to a very severe flood over Europe, but instead a heat dome this time. And it was 40 degrees C in many parts of the UK. It was 37.6 degrees in my garden in Newcastle, which is completely crazy if anybody knows the northeast of England. And there were records broken in many locations. This is important because we've been trying to work out whether large-scale conditions are important for producing hourly rainfall extremes. And when we've looked at this in the past, we found that 40% of heat waves in Europe are associated with very extreme hourly rainfall events. And so what we wanted to do in some work by Anna Whitford, who's now at the UK Met Office, but she was one of my PhD students who finished a couple of years ago now. So she looked at the top 20 UK rainfall events. So looking at observations, pulling out the biggest 3-hour rainfall events in the UK in the summer. And looking at looking at the meridional wind anomalies from a climatology for those top 20 events, and then she took a composite across those anomalies. And I don't know what you would expect as an audience to see when you take anomalies for these very small scale extreme rainfall events that cause flash floods. They're quite localized events. What we certainly didn't expect to see is something as large scale and structured in the atmosphere as what we're seeing here. So what we're seeing here as we move from 5 days before the event, or the 20 events, to 4 days before, 3 days before, 2 days, 1 day. As you can see, this development of this Rossby wave train in the atmosphere, it's very, very clear. And then on the event day itself, you can see it's basically staying quite stationary, this train, in the same locations, and then it breaks basically, and you get this rainfall event. And that's really interesting because it means that these very extreme sub-daily or hourly rainfall extremes in the UK are caused by very large scale climate dynamics, which is not necessarily what people expect and what people believe happens. We looked at this as well for other parts of Europe, Germany, France, etc. You get the same sort of signature spatially for other countries as well. So the other thing we then looked at is the synoptic situation across these 20 events. And again, we've taken a composite anomaly from the 45-day climatology. And again, you can see now if we move, from 7 days beforehand, 6 days, 5 days, you can see basically you've got this blocking pattern setting up across the whole of the Northern Hemisphere and particularly across the Atlantic. And this high pressure is catching up gradually with low pressure, and you can see you've got a stationary high over Scandinavia here. And then as you come in, it's very stationary but gradually catching up. The event day itself, and you've got cut-off lows here and here now, and then you gradually get this intensification of this low here and the dissipation. And it's really, really very interesting that this large-scale blocked pattern is something that produces these very intense rainfall extremes across, as it appears, most of Europe. The other thing we looked at is the mean temperature anomaly on the days surrounding these top 20 3-hour rainfall events for the UK. And we found something interesting as well, and this is the link to heat waves that, again, I guess perhaps from previous work we might have expected to find this, but perhaps not to the strength that we did. So in previous work by one of my PhD students, Christoph Sauter, we found that 40% of heat waves are followed by hourly extreme rainfall. But, we didn't really understand the mechanisms completely. But you can see here, as you move from 4 days beforehand, the heat anomalies, 3 days, 2 days, you can see this build-up of heat from this block over Scandinavia to 1 day here. The event day, where you get the most intense heat. Then the heat wave slowly starts to dissipate towards the east here 1 day afterwards. You can also see the cooling effect of perhaps rainfall happening here and here from these cut-off lows. And then eventually the heat wave dissipates. And again, on the event day itself, we're seeing this hourly extreme rainfall across the UK. And if you're interested in this, I'm not going to go into this detail now because I think you're probably the wrong audience. But if you're interested in some of the details of why this happens and the mechanics of this, in particular related to weather patterns, then do go and read a paper that Paul Davies led in Weather and Climate Extremes last year, where we produce a new conceptual model for how these rainfall events actually occur. In terms of the atmospheric layers and the lifting that's needed, and then how that actually relates to the large-scale atmosphere in terms of the transition between, this is a weather pattern, regime 5 to regime 6, and then how that produces these sub-hourly rainfall extremes, but also the relationship to the high pressure as well. And again, you can see that this is exactly the signature that we saw with Storm Daniel in 2023, where you saw this heat event, you see these cut-off lows, and then up here you see these very intense hourly rainfall as well. And again, we saw the same type of system in the German floods in 2021. So there's a lot going on weather extremes are increasing. There's lots of links between different types of extremes, and they happen in sequences, both regionally and I would argue at least hemispherically. But do climate models adequately simulate the changes to heat waves, extreme rainfall and flooding that we're actually experiencing in the real world? So this is a nice paper that was published by Rusi et al. In Nature Communications in 2022. And what they showed is that there are increasing heatwave trends over the mid-latitudes and Europe. But actually Europe is showing a much an enhanced trend in heat waves and in the intensity of heat waves compared to the rest of the Northern Hemisphere. There was a follow-up paper by Robert Voltard in Nature Communications in 2023, where they actually looked at how well climate models are simulating these trends in heat waves in Western Europe. And what you can see here is that the observations here, so the observed trends in the heat waves, so this is from ERA 5 and from EOBS, which is a gauge data set or a sort of instrument measurement surface observations data set. You can see that they've split it into dynamical trends and thermodynamical trends, where they've looked at the influence of the large-scale atmosphere and the temperature change. And you can see they've compared the trends in the CMIP6 models to what's happening in the observations. What you can immediately see is that all of the CMIP6 models are underestimating the trend in the large-scale atmosphere that's contributing to these heat extremes in Western Europe. So you can see the observations are here and all of the models are much lower. What you can also see is that most of the models also underestimate the trend in temperature as well, temperature change. And so basically the models are underestimating the increasing rate of heat extremes in Western Europe because they're underestimating in particular the trends in atmospheric circulation, these blocking events that we're seeing in the real world. And I guess this perhaps we should have expected this. So there was a nice paper by Reinhard Schumann in 2020 that looked at the persistence of long-lived blocks in climate models and found that basically as we improve our models, so we're moving from CMIP5 to CMIP6 and for different resolutions of models, basically the models underestimate the persistence of blocking quite significantly compared to the reanalysis of the observations. And it doesn't seem to improve very much, at least down to 25 kilometer resolution with the resolution improvement. Maybe that'll be better when we get down to kilometer resolutions or these convection-permitting scales. I don't think we know, but that's the hope. But at the moment, we know that climate models underestimate the persistence of these blocking episodes. And that's because they don't simulate this waviness that we seem to be seeing more and more of in the jet. So they're underestimating the persistence, they're underestimating therefore they're underestimating the heat waves as well, and therefore almost certainly these major flood events that we're seeing in Europe and other parts of the world. So the other thing that they are underestimating as well is James Carruthers, who's just finished his PhD with me and is now doing a postdoc. For his PhD, he looked at changes to UK mean winter precipitation, and he produced this really neat method by which he basically used weather patterns to remove for each weather pattern, he worked out what the mean daily rainfall would be for that weather pattern in the winter. And then he took that away from the observations. And so basically you can take away the dynamical contribution to monthly and seasonal precipitation. And when he did that, he got this dynamical winter precipitation here in the red, the observed winter precipitation from 1900 to present day is in blue. And then you get this basically this difference here. And you can see that it starts to rise after about 1980. And that's highly related to this temperature anomaly that we see, particularly since 1980. And what we found was that UK mean winter precipitation has increased at 7% per degree of warming since 1980. And you can see this again on here. So this is the precipitation anomaly for observations in the UK. And this is again a slide that I showed at the National Emergency Briefing. And you can see here as well what climate models project all the way out to the end of the century. And you can see this big difference between what the observations are doing and what the CMIP6 global climate models are doing. And it doesn't matter, actually. This is for CMIP6, but it doesn't actually matter whether you use CMIP6 or whether you use the UK CP18. They all underestimate. If you use a global climate model, they underestimate the observed changes in winter rainfall quite significantly, such that the changes that we have already observed are not observed till the mid-2040s. So they're about 25 years behind where we are now in terms of their predictions. And when we look at what change in rainfall we've seen in observations, we're seeing something like 30 millimetres of extra winter rainfall across the UK. And that doesn't sound like a lot, but it's 7.3 billion cubic metres of extra water, which is 3 million Olympic-sized swimming pools every year. And of course, that has a huge impact on soil moisture levels and flooding. And it comes as no surprise, I'm sure, to anybody that when you start to look at the patterns of this accumulation of this precipitation anomaly compared to regional trends in river flood discharges, you get quite a close correlation. So climate models are underestimating observed rates of change. So ultimately, we need to produce better climate models, or do we need different approaches to actually provide information for climate adaptation? I'm certainly not convinced that climate models will ever provide all the answers we need, and maybe we shouldn't expect them to. They are models after all. So I think one of the important things that we need to do is we need to connect information from different types of models. So we need to use information from weather forecast models, a bit like we've used these convection-permitting models, but also in weather forecast mode. And we also need to include observations and what's happening there to constrain our predictions, and use our expert judgment as well, and our physical and theoretical understanding to understand what biases there are in the climate models. One of the nice ways to do this is actually using storylines, and I think that this is probably one of the only ways we can do this actually with the underestimates we're seeing in climate models and the biases as well. And this is a figure from one of Ted Shepard's papers, but I've changed it because this is what, well, the blue is what he thinks is important. I've added some things in red because I think that for me, and this is something that I'm going to look at in my Faraday Discovery Fellowship, I think what's really important is we don't think about these natural modes of variability, and actually they matter a lot, and we think that they're predictable on much more predictable on different timescales than models are able to actually simulate. So we're going to be developing a new approach to looking at these natural modes of variability and trying to produce predictions of extreme events from real time out to multiple. See here that the models are underestimating the observed rate of change, and you get this pattern of increases in Northern Europe in winter precipitation, and therefore obviously it relates to flooding. But the climate models are very much underestimating those. I think that what I'm suggesting and what I'm going to be following in my fellowship is very much a drivers, regimes, events approach, because I think I've shown you today that very much multiple hazards happen in sequences, and they're caused by these regimes. And we're interested in drivers as well, because we think that drivers at different time and space scales, things like ENSO through to, say, the QBO or the MJO, all combine to in predictable ways to form these natural modes of variability. And we're going to use this new understanding to try to produce storylines of plausible extreme events, and also to monitor changing risks of extremes and probabilities of extremes, as well as trying to improve seasonal forecasts out to climate model projections. And this just shows very briefly what I'm planning on doing in my Faraday Discovery Fellowship, and one of the figures that I put in my proposal, really showing how all of these different things connect together. So the idea is to produce this seamless framework for predicting hydroclimatic extremes, and I've got 10 years to do this. So hopefully they will come out with some results in the next few years that will help people to plan for these extreme events and hopefully provide advance warning of them as well. So I just wanted to say, if we return to what I talked about at the beginning, very much the UK's preparation for climate change are inadequate. The Climate Change Committee have said this in their latest progress report. They've been saying this for years, and there is a need for new thinking and for adaptation planning from the government in the National Adaptation Plan that sets clear, measurable objectives and actually integrates climate resilience into all major policies. And the major thing that they need to do is really to deliver adaptation. They can plan as much as they like, but we need to be delivering adaptation with the investment in this space to back it up. And if we don't do it now, the costs will be much greater later. And I wanted to finish by just thinking a little bit about what type of extreme rainfall could we get in the UK. So how extreme could extreme rainfall get? So in Valencia, as I've said already, they received 760 millimetres of rainfall in 24 hours. So that's more than the annual average rainfall in 24 hours. In parts of Austria, in Storm Boris, they received 2/3 of their average annual rainfall in 3 or 4 days. In parts of Greece, in Storm Daniel, they received almost 2 times annual average rainfall in 3 to 4 days. In that paper that I discussed earlier, we showed that hourly extremes can intensify by about 21% per degree C and whole events by 7 to 14%. But, you know, if we got one of these events at the moment in the UK, and there's no physical reason why we couldn't get one of these blocking cut-off low events in the UK, we'd be looking at, say we received the same sort of rainfall as Austria in Storm Boris, 2/3 of their annual average rainfall in 3 or 4 days. You know, in London, that could look like 400 millimetres of rainfall. And we'd be less likely to get one of these in Scotland at the moment, but, you know, you can get crazy amounts of rainfall over very, very large areas, and quite catastrophic flood events resulting, which we've seen a number of times in Europe in recent years. And the extent of the catastrophe is actually unimaginable. I mean, to think about it, then Storm Claudia in Monmouth, the floods that we saw, that's about 1/3 of the rainfall we could expect from one of these types of events, if we have one. So I think, in summary, we need to understand multi-hazard risks for adaptation decisions. There's not been enough work done so far. We really need to understand the global to local drivers. Climate models really don't give us all the answers. We need to be very careful about how we use their outputs and which climate models we use, actually. And one of the things I haven't said is that convection-permitting models do produce much better estimates of change than global climate models. So when we're thinking about, for example, changes to winter rainfall in the UK, they produce much more realistic rates of change. So we need to be thinking about what we're using and why, and really being careful that actually they're producing realistic rates of change. And I think storylines provide a really good way to combine the evidence and support decision making.
And if you're interested, there's a reference to a book there that we published open access in the summer, which looks at all of these aspects of uncertainty and climate change research. And it really was a labour of love, led by Linda Mearns, who's sadly no longer with us, but it's taken us a decade to get this out. All right, thank you very much.